Hey, we've got Codeforces Round 805 Div 3 today. Let's get started. Power of 10 is round number. Okay. Uh, I didn't get a 0. Submit. Unfortunate. You can learn 3 letters. It's just the number of... Oh, it's not quite that. You actually have to... Or scene. Oh, that was really hard. A to B? Basically, does this occur before this? Oh, okay, that's basically. Oh. But yes, deeds very easy. You just have to reconstruct this. Oh no, that is not right. It's index. Oh, what? All the dominoes. So, oh, there are 1 through n, so there's n dominoes. So there's 2 numbers. N has to be even, first of all. So even, okay. If two things overlap, they have to be opposites. Okay, that's fine. It's just this. Oh, it's just yes. It's just a yes now. Okay, so we can do this. Alright, so now yeah, okay. So my otherwise we're gonna solve it. We're gonna basically each component oh, is that it? You don't have to construct it. Give a yes for this. Oh. That's very tricky. Something here that you can get a. This Q is unfortunate. Do you know what it should be? Okay. Let's see. So working in A, we can divide it by 2 until you can take it to its odd. So every number in A, we need a number in B where the prefix matches. So then for every So I think we should just do this greedily and take the longest frequency is an A. If something can match a shorter one and a longer one, we should take the longer one because something else could match the shorter one, but not the longer one. So I think that's it. I think we can just do like a try. Okay, now we're gonna put everything from B. I should have had a binary try. Okay, essentially that's what we're supposed to do. Anywhere there's string, I'm gonna replace with int. Okay, so Alright, that's F. So again, we're stuck in Q. Identity is finished. Let's read G. This is the number of queries. 5 queries, 2 to 5 queries. Passes through each vertex. That means it's a path. Oh, they actually say that. Okay. I see. So take the LCA of all the nodes in your set, and then that's the highest. Okay, yeah, I got a wrong answer. What's this? Okay, what's wrong with this? Oh no. Okay. How do I pass the samples? I gotta stop doing that. Okay, so this is pretty easy, I think. Just take this and then converts. Just be 1. Alright, so I have the ancestor, and if V is on the path, we'll start to ants. Continue. Or end. If start is on the path from ants to V, end is on the path. It's wrong. F is still wrong. What is going on? Why am I failing everything? 2, 3, 5, yeah, okay. Oh, will they branch later? Aha, okay. So it's basically that. I don't know. Okay, now what's wrong with F? Oh, I need to subtract up the tree as well? I'm so bad. I'm so bad. 2 wrong answers. $51, so we at 138. Wow. That's a lot of things. All right. All right, you're gonna go through and talk through each problem. I haven't done one of these in a little while, but it'd be nice to do one. All right, so let's start with problem A. Basically, this problem, we are trying to round down to a power of 10, taking in a number from 1 to 10 to the 9th, and see how much we have to decrease the number to get to a power of 10. And so the way I did this was to just read the number as a string, and then you can build the power of 10 easily by starting with a string with zeros and just adding a 1 at the beginning of the same length. And I use STOL, which is string to long, or stol, which is also a word, I guess. Just converts the number from a string to an actual integer, and I can just subtract. So that's A. Problem B. Problem B was very tricky for B. I'm not really sure if there's something much easier than what I did, but basically, what I missed here was that I thought once you remembered a number, or a letter, you remember it for good, but actually you can see here that this G is not free even though you had a G here. So basically you need to divide the string up into chunks where each chunk has at most 3 distinct letters, and you want to make it the fewest number of chunks possible. So the solution is just greedy. You just kind of go forward while you're not going to go over 3, and kind of eat as many characters as you can. So for this string, you eat the first 3, and then you're stuck because the next one would be a 4th. The next, you eat the next 3, and you're stuck because the O would be a 4th letter. Then you can eat these 4. Notice that the O repeats, so it doesn't cost you an extra one. And then finally you need to do the Y. So the answer for that one is 4. So yeah, this is just a simple greedy implementation. I have a scene array that tells me which letters have been seen, and I just keep going while either we have fewer than 3, or we do have 3, but the current character has been seen. And this is just kind of updating the count, marking it as seen, and going forward. Yep, so that's B. For C, yeah, we have a sort of trains path from U1 through UN. And we get queries A and B, and we want to know, essentially, is there any A in the U list that occurs before some B in the U list? So if this is your list, then 3 and 5 will be true because this 3 occurs before this 5. 1 and 7 will be false because even though we have both 1 and 7, the 1s all occur after the 7s. And then 3 and 10 will be false because 10 does not appear. So this one, the idea is fairly simple. I just keep track of the first time I see any number in the list and the last time I see any number in the list. And so I just want to compare the first time I see A with the last time I see B. And that's basically what I do here. I use two maps to track that, and then we succeed if A is in the map and B is in the map, and the first A comes before the last B. All right, let's talk about D. So D, you have a string, and then each letter has a value between 1 and 26. You want to remove characters until the value is below, or is P or less, and you want to remove the fewest number of characters. So this is a simple greedy. You obviously always remove the highest value character every time until you get below P, or less or equal to P. And you just need to output the same string in the same order. So what I do is I take all of the characters in the string and sort them, and I keep the index with them so I know where the index comes from. And while my sum is over P, I will take the next highest character and remove it. And I will replace it in the string with a dash. And so finally that way when I build my output, I can just go through the string and add anything that's not a dash and output that. Yeah, so pretty simple greedy idea. The main thing was just reconstructing. It's easy to solve the greedy if you have, a frequency table of everything A through Z, but that makes it harder to reconstruct the string. You can still do it, like if you know how many versions of each character you want, you can go through the string. You could do it in 26 times n time, but this is also another way to do it that's efficient. Okay, problem E. So we have a bunch of dominoes, and we want to split into two sets so that in each set, all the numbers on all the dominoes are different. And there are n dominoes, and the numbers are between 1 and n. So immediately we notice that there are 2n numbers listed on the dominoes, because 2 per domino. And we need to split it into two sets, so each set will have n numbers, which means also that n needs to be even. And if n numbers that are between 1 and n are all different, it has to be exactly a permutation of 1 through n. So what that also tells us is that each number 1 through n has to show up twice. So that's the first thing you can check here. If anything shows up more than twice, it's a no. Also, one little tricky case, if any domino has the same number on both ends, it's a no, because that domino will end up in one set and that will have to repeat immediately. And then otherwise, how do we know whether it's possible? Well, if two dominoes overlap with a number, they have to be in opposite sets. And if we took those conditions across all pairs of dominoes, that would actually give us our exactly necessary conditions to solve this. So that's basically what I do here. I build a graph. It turns out the graph, because of the fact that no number shows up more than twice, the graph doesn't have too many edges. So for example, this domino and this domino would have an edge because they share a 1. This one and this one would have an edge because they share a 4, and so on. So essentially I just keep track of, where's the other domino with this number? And I add the edges based on that. And this is pre-written code that checks if the graph is bipartite. We need the graph to be bipartite in order to solve, because we need to split it into two sides where there are no edges inside a side. And so yeah, that's the idea there. If you haven't heard of bipartite graph, just look this up. All right, problem F. Yeah, this problem, I kept messing up the implementation, but basically, when you have these two operations, multiply by 2 and divide by 2 rounding down, essentially what you're saying is you can, if you look at the number in binary, you can take any prefix of that number and then you can add any number of zeros that you want to it. Because the way we get there is we divide by 2 until that exact prefix is the number, and then we can multiply it by 2 as much as we want, which is adding zeros to the end. And then you can notice that adding or removing a 0 are both at the end are both reversible operations. So you might as well start out by removing all of the trailing zeros from all the numbers. So we can, essentially we can canonicalize each number to its odd prefix. So if we have 24, we would bring it down to 3. If we have 5, it stays as 5. If we have 4, it goes down to 1, and so on. And then we end up with a bunch of numbers, you know, in A. We have a bunch of numbers in B. This is not a good example, but it's a good example. Yeah. A bunch of numbers in B. And we want to map each number in A to a number in B, where the number in A is a prefix of the number in B. Right? And not every greedy idea works here. You can't just grab any number in A and map it to any number in B, because if you mapped this to this, you would immediately become unable to map this number, because this is only able to map here. But that gives us an idea where the only way we kind of obstruct ourselves is if we map a shorter number first, which prevents a longer number from being mapped later. So the greedy idea is to map the longest numbers first, basically go through A in decreasing order of length and map those to anything in B. Because the reason is, if you were going in decreasing order of length and you map them and you have a couple different options for what to map to, it doesn't matter what you pick, because every other number in the future that you want to map is going to be shorter. So if something matches your current number now, then if a number of options match your current number, like if we have a number of options in B that are that start with this, then in the future, any prefix of this, for example, all of those will still be candidates. So we can just pick anything. And the way I implemented this was with the try. And you can actually just sort A reverse numerically, which is nice once you do the canonicalize step. Yeah, and I kept messing up the implementation because I messed up the words counting in here. But otherwise, it wasn't too bad of an implementation. I don't really like how the erase went, but I guess... Oh, I guess I don't need to do this, do I? Okay, maybe I can simplify this, because I think... Because I'm going... in decreasing order of length. I'm going to erase up 2, and that's just this. Let's try submitting this, actually. Might as well, since it's ICPC setup. Yeah, it looks like it worked. Okay, so that can simplify it for this because of the constraint. But yeah, anyway, that's problem F. I'll probably go back and clean up the try stuff later. And finally, problem G. Actually pretty easy to describe. So you have a tree, and then you have a bunch of queries. Each query is a set of vertices. So for example, 3, 2, 5. And you want to determine, is there a simple path that contains all the vertices in this set? So the way that, for example, 3, 2, 5, you do have a simple path because you have 3 to 5 as the path. Whereas if you have a query on 1, 3, 5, then you do not have a simple path because there is no path containing these union nodes. So yeah, essentially what I did is I start by finding the LCA of all the vertices, and that's kind of the top of the path in a sense, and then you can have 2 other ends to the path, sort of a left lower end and a right lower end. And I just go through each of the vertices, and essentially if you have a new vertex, you can kind of fit it into a couple cases. If it's already in your keeping track of the left and right ends, right? If it already is on the path from the left to the right, then you can just move on and you can skip it. I really should have done this actually. Otherwise, if it's not, we're going to need to extend one of the two ends. And the way we know this is either the start end is going to be in between ancestor to V, or the end. Either start is between ancestor and V, or end is between ancestor and V. And in those cases, we need to either extend start to become V or end to become V. So we're kind of keeping track of the how far down each end of the path needs to go. And then finally at the end, we need to make sure that the LCA of start and end is actually our original LCA, because otherwise we get a case where the LCA is 1, we get start as 3, end as 5, and we call that a path. But really the LCA of 3 and 5 is 2, which is a problem. Well, that's pretty much it. That is the algorithm here. This is very efficient. This is like linear time per query, I think. Oh wait, this on path might be. No, this is actually constant time. Yeah, so it's very efficient per query. And I'll just select this again as well. Yeah, okay. So that looks good too. But yeah, all in all, kind of messed up on F with all the extra submits. This cost me another, like, how much? 11 minutes of actual time and 20 minutes of penalty, so like 31 minutes of penalty. But it looks like I still got top 10 here. Should have been more around here if I had messed it up, but no big deal. Cool. Anyway, thanks for checking out the video. I know it's been a little while since I did one of these, but it's nice to do another one. And I'll see you in the next one.